Today we'll discuss about the solution of linear programming problems. Linear programming problems are the problems of optimization, either to maximize or to minimize. The general form of a linear programming problem is given by first an objective function. Objective function means it is a linear function which is to be maximized or minimized. Linear function which is to be optimized, that is known as objective function. Here we are writing the objective function z equal to c1x1 plus c2x2 up to cnxn. Then we have constraint attached to it. The constraints are the linear inequalities of a linear programming problem. These are the set of conditions under which this z is to be minimized or maximized. So the constraints are the conditions under which the given objective function is to maximize or minimize. Then third we have non-negativity restriction. Non-negativity restriction says that the variable can't be negative. So this is a general form of linear programming problem. First objective function, then the set of constraints, and then the non-negativity restrictions. Now in any linear programming problem, we get a set of variables which are satisfying the non-negativity restriction. The set of variables or any solution which satisfies the non-negativity restriction is known as feasible solution. Out of those feasible solution, any of the solution maximizes or minimizes the objective function. That is known as optimal solution. The solution which optimizes z, the solution which optimizes z is said to be optimal solution. Suppose we draw the graph of a linear programming problem and we get such type of graph for the linear programming problem. When we shade the region satisfying the given inequalities, we shade the region satisfying the given inequalities. Suppose this region is shaded. This region is known as feasible region. The region which is satisfying the inequalities given is known as feasible region, and the region other than this is known as infeasible region. Now this feasible region may be bounded or unbounded. If the feasible region is finite, here we have a finite feasible region, it is bounded. And if the feasible region is infinite, it is extending up to infinite. This is known as unbounded feasible region. This is unbounded, and here we have bounded feasible region. So the solution region which is satisfying the given constraint is known as feasible region. This feasible region may be bounded or unbounded. If it is finite, it is bounded, and if it extends up to infinite, it is known as unbounded feasible region. Here we'll solve this linear programming problem. First, take the first constraint. Here we have to put equal sign so that it becomes x plus y equal to 50. Now we have to draw the table for it to draw the graph. We'll put here x equal and y. If we put x here 0, if we put x 0, we get y equal to 50. And if we put this y as 0, we get x equal to 50. Now the second constant is 3x plus y. Here we have to take equal sign and 90. X and y. If we put x equal to 0 here, y is 90. And if we put y equal to 0 here, x will be 30. Now we draw the graph of this. Here it is 10, 20, 30, 40, 50, 60, 70 and so on. Here it is 10, 20, 30, 40, 50, 60, 70, 80, 90 and so on. First we mark the value 0 and 50. This is 0, 50. Then 50, 0. 50, 0 is here. Draw the line. This line is obtained. For this inequality, we are having less than sign. Since here we have less than sign, we have to shade the region below this line. This is the region below this line. Then draw the line for this one, x0, y90 here and y0, x30 here. If we draw the line of this, we get this line. This is also having less than equal to sign. So the region below this line. Now the third line is for x equal to 10. Here is the line for x equal to 10. This is having greater than sign, so the region right side to this. This is a common solution region we have obtained. In this common solution region, there are 4 corner points, 1, 2, 3 and 4. Here it is A. Coordinates of A are 10, 0. Here it is B. Coordinates of B are 30, 0. Then here it is C. Coordinates of C are 20, 30. And here it is D. Coordinates of D are 10, 40. These are the 4 corner points obtained. Now put all these values in Z. Z at A. 4 into 10. 4 into 10 is 40 plus 0, which is 40. Now put this value ZB. 4 into 30. 120 plus 0 equal to 120. Then put this value 4 into 20, 80 plus 30, which is 110. 4 into 10, 40 plus 40, which is 80. Here it is a problem of maximization. This is the maximum value. So we can say Z maximum equal to 120 at x equal to 30 and y equal to 0. Now we take the another problem. Minimize Z equal to 6x plus 3y subject to these 3 constraints and non-negativity restrictions. First we take first constraint is equal to 0. We put here x0, y obtained is 80. Then we put y0, x is 20. So this is the table for the first constant. Now table for the second constant. we put x 0, y is 23. Then we put y 0, x is 115. Then take the third constraint, 3x plus 2y equal to 150. Put x equal to 0, y is 75. And when we put y equal to 0, we get x equal to 50. Now these are the three table. From these three tables, we have to draw the graph. If we draw the graph, we get these three lines on the graph paper. Here we are having greater than sign, so the region above it. Here we are having less than sign, so the region below it. And here greater than sign, region above it. So the common shaded region is this one. It is common for all the three lines. Now at this point we are having three corner points. A is 40, 15, B is 15, 20 and C is 2, 72. From the graph we have obtained these three corner points. Now we'll put these values of the three corner points in the given function z. Firstly, we have placed A, that is 40, 15 in z. When we put these values of x and y in this z in place of x and y, we get 6 into 40 plus 3 into 15, which is 285. Then the second point is 15, 20. We put this value of x and y in the given function z, we get 150 answer. Then the third point 2, 72, will place these values in this z in place of x and y, we get 228. Since it is a problem of minimizing, so the minimum value obtained is 150. So the z minimum is 150 at x equal to 15 and y equal to 20. This is the solution of this linear programming problem. We'll solve this linear programming problem. Maximize z equal to 20x plus 10y subject to the constant 1, 2 and 3. First we take the first constraint. We'll put here equal sign. We get x plus 2y equal to 28. Now we have to draw the graph. So we make the table. Put x equal to 0, y equal to 28 upon 2, that is 14. Then we put here y equal to 0, we get x equal to 28. This is the table for this equation. Now we draw the table for the second equation, 3x plus y equal to 24. If we put here x equal to 0, y is 24. And if we put here y equal to 0, x is 8. So this is the table. Here we are having only one variable, x equal to 2 will be a straight line parallel to y-axis. Now we draw the graph of this. When we draw the graph of this, we obtain such graph for all the three lines. It is for x equal to 2. Since here it was x is greater than equal to 2. So we have to take right part of this line. In this equation we were having less than sign. So the part below this line. And for this equation we were having greater than equal to sign. So part above this line. This is the common portion of all the three lines. We have shaded this common portion. Now in this common portion, we will take three corner points. These are the corner points A4, 12, B2, 13 and C2, 18. These are the three corner points obtained by us. Now we'll put these values of the corner point in Z. First point is 4, 12. When we put this point in this given Z, For x and y, we write with this value of 4 and 12. We get z equal to 200. Then the second point is 2 comma 13. When we put this value of x and y here in the z, we get 170. Then the third point is 2 comma 18. When we put with this value of x and y here in the z, we get 220. Since it is a problem of maximize, so we have to look at the maximum answer. The maximum value of z obtained is 220, which is at x equal to 2 and y equal to 18. So this is the solution of this linear programming problem.